So we saw this program. Okay, so less pgm1.asm. So we printed and we asked for input, correct? So we took some message and ultimately we tried doing so. So we asked for input, then we made the changes in the code and appropriately got the thing. Now the command that we applied to say translate the code was, or rather what are the steps? We wrote a program, we gave extension to that program as ASM. Okay, we tried making use of instructions. So like my role is not to talk about instructions, okay, but ultimately we'll be requiring them rather to really address the translation part of the system. Correct. Now what exactly happens at that point of time? So what we did was we wrote a program. So program had some form, okay, where we divided our code into some sections. So probably it could be RO data, BSS, data, text. You may or may not prefer to make use of RO data, but you definitely can think of rather you have to definitely take section.text. So the important thing that would be writing is section.text, global main, and then this main. Rest of the things would be dependent on what exactly you are going to do with the code and what exactly you would be achieving. Fine. So now the way that we saw, there is a journey of a code rather from .c to a.out. There were few important aspects involved. So similarly, so if I write NASM FELF32, okay, so my program name .c, sorry, my program name .asm. So this is my mechanism to generate .o. Correct. So I can see that it generates me .o, and then I would be writing GCC-M32 this pgm1.o to get an executable. Correct. So these are the two important commands that I'm going to fire. So first one was this, and second one was this. Fine. So if I see rather the file sizes, similarly the way that we saw, like program one.asm had 430. So when we generated .o, it gave us 896. Note that output of assembler would be .o only. So if I really wish to see the pre-processed version, so you can make use of this -e2. So say, let me see if I can write less. So this is pre-processed version. You can see few things are added there. So most of the things would be included into say like % thing. Okay, as well as some square bracket would be involved there. And then ultimately your code occurs. So this -e is meant for pre-processing. Fine. Now when we go along, like for example, whatever the strategy that was applied to generate the code which was an object code. If I see, I can see that my code was translated. It had some address. Okay, so if I see my code, this is where my code is. So it had a few bytes dedicated to generate an object code. Now, if I want to see like what exactly the process applied there. So if I see here, it added some thing here. Actually, this is not what I wrote inside the code. I haven't written any push, JE, INSL kind of instructions. So my code was pretty simple to have contents to be like this. Correct? So now instead of saying this disassembly, reverse of assembly process, can I really see what exactly assembler did with my code? So for that purpose, you have to simply write this. So write -L and you list. So this generates you listing. So suppose I am giving pgm1.lst. So this pgm1.lst would be generated. So now it will have this message translated. So one can see here MSG. This is my first assembler and see the execution. This is my first try to use assembler and see the execution 10-0. So this looks to be the complete translation. Correct. Now I can see that there is %d and 0. percent D 0. Then value is percent D 10 0. So if I see here in these three cases, I have used 0 and 10. Okay, here two cases at least I have used 0 and 10, and one case I used 0. So I can see that this 0 was meant for that. 0A was meant for 10. So 0A 0 0. Same case I can see here. That means what? This whole stuff, like including this and this one, was meant for this statement. Okay. Similarly, if I talk about this 0 was here. So these three things are meant for this percent D and 0. Correct. Now, if I try to really see the comparison, so VAL third value is L, correct? So if I see here, if I write say V is this 56, 41, 6C. So if L is 60, 6C, so where is my L? So assembler, correct? Let us see this. So if I try to compute this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, it would be better if we take I for a while. So third one. So if I see 54, 68, 69, what is this? I is 69. Same case I can see here before percent D. So if I see percent D was 2564. So this is 2564 percent D. Then there is a space. So this 20. Correct. Correct. After before that percent D, this was the space. Then there was S. So 73. And then I had 69. So if I see here THI, so I started here T H and I was 69. So I can see that 69 got here. So how exactly this is written then in the code? So let us try to write a simple code for today. So Emacs pgm2 dot asm. And actually we are starting work of the translation. So let me write section dot data. So you may write arrow data or data. So my message. So let me write this db and let me write disk A B C D E F G H I J K L M N O P Q R S T U V W X Y Z. And let me simply write section dot text global main and simply write one instruction. So NOP, no operation. This is one of the instructions. So you save this data. Now our target is to see how this translation is done. Okay, this A, B, C, D and so on. Let us try to see how this encoding at machine code at machine level by my system is done. Right? So this is our code we had. Correct. Now let us try to translate this and we will generate .lst for the code. So the command that I'm firing is nasm-falf32 program.asm -l program.lst. So if I open now pgm2.lst. Now see here. So you can see these are consecutive ones, correct? So I can see here numbers 41, 42, 43, 44, 45 and so on. And towards like last is Z. So Z is 5A, then 10, 0A, then 0, 00. So now each pair of digit here represents one character there. Represent one's character. Now this is in what system? What is what you can say ASCII value for capital A? Do you know that? What is
65.
Very good. Try to convert that 65 to hex. What you are getting? Convert that 65 to hex. What it would be? Correct, 41. Can you see that 41 there? So now what would be for small a? What is small a? ASCII value for small a? 65 plus 32, correct? What is small a then?
97.
97. Convert that 97 to hex. And let us see whether are we getting the same one. Convert that. What it would be?
61.
61. So 45. Let us see. Can we see 61 here? Yes. So that means what? We actually successfully could understand in object code what is written there. This was the object code. So addressing started from 0. So see how many characters are there? If you compute 1, 2, these are 26. Correct? 27, 28 characters. If you try to convert 28 into hex, what would be the representation? 28, na? 28 to hex. क्या आएगा? Convert 28 to hex.
1C.
1C. Can you see this 1C here? So if you add now 26, 28 again with 1C. So if I go on, sorry, if I go on from here, 1C, 1D, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Correct? So next would be what? 38. So if at all I do write something, say let us try that. So if I add something here, I say MHG2 dB. Can you see 38? Because we started from that one. So now you got this thing for ASDF again. Now this is how your ASCII characters would be translated. Now these not would be taken as ASCII, these would be taken as digits. 10 is converted to 0A and 0 is converted to 0. Now if what happens then if I write numbers inside double quotes? Instead of this now I am writing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Correct? Now this 0 that I have here and this 0 are different. Are they? Yes, one of them is string, other one is, or one of them is character, other one is a number. So if I try to translate that now, see, this was 30, 30, 31 and so on. 39, 9 digits, total 10 from 30, considering 30 to be part of it. And then 0 is 0, 0. Now suppose if I hide this part from you, if I hide this part from you now, will you be able to tell me, like with assumption that this is not there? Okay. Will you be able to tell me what exactly they are? You should be able to. Now you should know what exactly I have to do. Reverse engineering, reverse analysis. So you definitely can come up with that because see, this would be hex. Convert that hex to decimal. Now try to find out which is the character value representing that decimal value. That would be your part of double quote. Part of double quote. So this is how translation for string values would be taken. Now let us try to see how exactly the numbers are translated. I assume you are with me.
Yes, sir.
Yes. Okay, good. Because now it would be important for us to really pay attention. Let me take MHG3. Let me take DD. 10, 100, 1000, 10,000, 1 lakh, 10 lakh. Okay, let us take these values. Now see, let us see what exactly happens there. How it is translated. So 10. I think this is 0A. So it took only 0A. Is it 0A? Actually, it took this whole thing. How will you write? Like, is it really this way? Is it really this way? Do you, if you have to convert this 10 and it consumes 4 bytes? So let us see how many numbers are there. 1, 2, 3, 4, 5, 6. So 6 multiplied by 4, 24. So 1. Okay, 1 I meant to say 4, 4, 4. 4 किधर जाएगा 64 क्या this one 4 then this 4 then next 4 and then last 4. You can see all 6 numbers are taken care of. 1, 2, 3, 4, 5, 6. Yes. Can you see that? If you try to like, okay, I don't know. I thought, okay. So this is 0A, 10. But do we write that way? How will you write 10 in 4 bytes? Your number will be something like the 0, 0, 0, 0, 0, 0, 0, 0A. Correct? Am I right? Yes or no? Or will you write this way? 0A, 0A, 0, 0, 0, 0, 0, 0. Now, what exactly this is? There is a mechanism applied by Intel architecture to store multi-byte data. Whenever it has to address multi-byte data type, like which requires more than a byte, then the mechanism changes. Now let me simply show you that part again. Let us go here. Let me write MHG4 DW. Now because this would be taking 2 bytes. So if I write 10, 20, 30, 40, 50. Let us take this. Okay, let us try to translate this. Let us get LST. Now see here 10 means 0A. Now see how it is written 0A 00. 20 means 14. 30 means 1E. 40 means 28 and 50 means 32. Now whenever it comes into the place or when it talks about more than a byte size, that's what I'm saying. The processor is making use of a mechanism for storing multi-byte data types, which would be the probably integer, float, and so on, whichever is requiring more than a byte. So the time comes to really talk about what are the different mechanisms that are applied by the system to store this. Okay, to show you, say, or rather to make use of such kind of mechanism to store with. So we are talking about little and big Indian notation. Now it is used to store a multi-byte, not type, multi-byte data type. Mainly, which are they? Now, those who used, say, for example, Turbo C, you must have seen that for integers you take only 2 bytes. But whenever we do talk about Linux and GCC, probably integer consumes 4 byte. Now, what exactly happens is, let us talk about this little Indian first. Now, this little Indian is a mechanism used by a machine. So, which are the machine which is making use of this little Indian notation to represent multi-byte data type? Always last byte of binary representation of the multi-byte data type is stored first. This is important. Last byte of binary representation of multi-byte data type is stored first. So we had 10. So we wrote 0A. Correct? As hex. Now when it is a byte, a single byte to write 10, that's what we saw here. When we got this, this. So whenever we got this 10 and which was used with DB, we could see that it used 0A and there was 0. That's why that 0 was consumed. Correct? So now when this 10 is written as word, then how will you write that number as considering 2 bytes? So it would be like this 0, 0, 0, 0, 0, 0, 0, 0. This is 1 byte. Correct? 1, 2, 3, 4, 1, 2, 3, 4. This is second byte. Now we have to talk about 8 plus 2. So this is 1. This is 1. Correct? This is 10. Are you with me? This is 8 plus 2, 10. Yes or no?
Yes, sir.
Okay, now if it is 10, how exactly you will write? Now what happens is if you talk about hex numbers from 0 to A, sorry, 0 to F. F is 15, correct? 0 to 15 in decimal perspective. So to represent this 15 in binary form, you would be requiring 4 bytes. 1, 1, 1, 1, correct? And for storing 0, not 4 bytes, but 4 bits enable. Sorry, I made a mistake. I said 4 byte. I'm saying I wanted to say 4 bits to represent this 15. Correct? F. That means what? If at all I have to represent a number in hex. So depending upon the bytes required, I have to choose it appropriately. So in this case, what is happening? It is actually written as 0, 0, 0, A. So each position now in this case, each position here actually is consuming 2 bits. Sorry, 4 bits, not 2 bits, but 4 bits like this. So 4 bits, 4 bits, 4 bits, 4 bits. So ultimately resulting to 18, 4 plus 4 plus 4 plus 4. Now if it is, this 10 is to be stored as a double word. So how many bytes would be there? 4. 1, 2, 3, 4, 1, 2, 3, 4. So if I take this 0, then 0, then 0, then 0. It is 4 byte. Now in this case, number would be like this. Correct. Now I have to write that like for each pair of 4 zeros. So I'm differentiating it like this. Now how will I write this? 0, 0, 0, 0, 0, 0, 0, A. Now if I have to write this with a little Indian notation, I will start writing this byte first, last byte first. So okay, then now in this case, I will not be able to understand what exactly. So let me take an example here to demonstrate that part to you. Suppose you wanted to store a number 0x 1 2 3 4 5 6 7 8. Okay. Now how will you write this 1 2 3 4 5 6 7 8? It is a hex number. How many digits are there? Are they 8? Yes, 1 2 3 4 5 6 7 8 8. So you differentiate them like this. Now if I have to write this 1 2 3 4 5 6 7 8, how will I write that? So this with assumption that this number is to be written, then I will write first 78, then 56, then 34, then 12. Let me show you that part. So let us say in the code only we are making the change. So I am simply saying here MHG4 DD 0x 1 2 3 4 5 6 7 8. Now let us see how exactly this is represented. Oh, I would have written message 5. See this number. Where was our this one? 78563412. Can you see this? Can you see this? Yes.
Yes, sir.
So this is called a Little Indian notation. So this 0A, when it was written for a byte, it's okay. For a byte, there was no any issue. But when it took it as a 2 bytes, then actually it was this. So it actually wrote it as 0A 00, and that's what is happening here when we see this 10 0A 00. So last byte first, then you take in the reverse order. Correct? Are you with me? So what kind of notation it is now? Little Indian notation. Is that fine? Now the tactic, like when we say Little Indian, now what about that Big Indian? The Big Indian would be writing it in the same way. Now I cannot show that because our machines are Little Indian notation following. Our machines are Little Indian machines. So it will store this number as it is if it is Little Indian notation 1 2 3 4 5 6 7 8. Big Indian notation will write it like this. Correct? Are you with me? Any question?
Sir, could you pardon, please?
Yeah, so let me repeat. So every machine would be either having the mechanism to store a multi-byte data. Now the machine that I'm using currently, I cannot comment on what your machine is having type as, but you definitely can check it. So my machine is making use of this Little Indian notation. There are two notations, Little Indian and Big Indian. So these are used to store multi-byte data type. Okay, whenever we are talking about integer float. These are the representations. You can say representations used to store. So Little Indian is what? Last byte of binary representation of the multi-byte data type is stored first. So when we saw 10, when it was stored as a byte, we saw 0A. When 10 is stored with a word form, actually binary would be this. Correct? So if I take each binary position, if I write that binary position for four representation, 4 bits, I'm representing it by hex number. That's what we saw here. For 0 we have 0, for F we have 15. But if I have to consume, I will be requiring 4 bits to represent this. Correct? To reach to this level for 15. That's why I'm I'm representing each 4-bit position by a single number, hex number. So this 0 is hex represented for these 4 bits 0000. For these 4 bits, I have this 0. For next 4 bit, I have this 0. And for last 4 bits, I have A. Now I have to convert that into a byte. So this is a word. That's why I converted it. I wrote it into 2 bytes. Now to write into little in Indian notation, I will write it like this 0A00. Is that fine? Now if it could have been say big Indian notation, then my number will look like this only. But our machines are mostly making use of little Indian note. Almost all machines, what are the machines that we are having now or you are using now, would be making use of this little Indian notation. Which one? This one. Fine. So to make the life easy, I took this number 1, 2, 3, 4, 5, 6, 7, 8, which requires 4 bytes to represent. So I am dividing them hex numbers into separate digits 1, 2, 3, 4, 5, 6, 7, 8. So you represent them, each of them rather, by binary. So 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Then what will you write? 4, 0, 1, 0, 0. Then 0, 1, 0, 1. Then 0, 1, 1, 0. Then 0, 4 plus 2, 6. Yeah. 0, 1, 1, 1. Then 1, 0, 0, 0. Correct? Now what exactly you are going to write? You are going to write that reverse mechanism. So 0, 8. Then this, then this, then this, then this, then this, then this, and then lastly this. Now you try to convert each of the number, each of the binary representation to say decimal, or like rather you can not decimal but hex. Okay, so 8, this is 7, this is 6, this is 5, this is 4, this is 3, this is 2, and this is 1. Correct? Now you use write them simply like this. Correct? So like sorry, I wrote 87. Actually, it should have been because we are writing in terms of byte representation. Correct. So the way that I wrote here, like when we see this 1, 2, 3, 4, 5, 6, 7, 8. So it is picking this byte, complete byte, not a single digit position. So you pick it as a byte perspective. So instead of this last byte, we said byte. So this would be written as a first. This first byte from left, sorry, from right. This is second byte. This is third one. And this is fourth one. Because we have to talk about byte. They are 4 nibbles. So that's how we are getting 7, 8, 5, 6, 3, 4, 1, 2. Fine. So we don't see a big Indian notation, but rather if you at all you want to properly see this for a C code. OK, I will be passing one code to you probably after the session on WhatsApp group. Try that code on your machine so that you can really verify what kind of representation internally used. Fine. So for every representation that you see for a decimal value or hex value. Fine. So this was our code. Okay, depending upon the representation used there, dB, dW, dd, so on. So it would be taken. So if let us try to see now what is the mechanism applied for BSS. So this is for data. So even if say for example section dot data, and here you write RO data. That also is possible. So this is your RO data. Okay, till this. And that your section dot data. That also is possibly done. So whatever, these numbers are not constant because you may be using them. These are initialized values. Okay, so you may say what exactly I did here. I have written a single value. So this is an array actually I defined, which is of type integer, and it is having size of 6. In this case also size is 5. Okay, if I simply write 10, that also is possible. Like that's what we did. Even I have. Okay, this is a single value we gave for a double. Fine. Are you with me? Yes, please.
Yes, sir.
Should we move further? Now let us talk about BSS. Let me write this raise B1, A1, raise W1. This is reserve. Okay, reserve how many bytes? Reserve words, how many words? So A2 raised D1. We'll be using 3 for a while. Let us see how exactly it gets translated. Now it will have address. Okay, what is the size? 1 byte. So next address would be at 1. Next is address, next is of 2 bytes because it is word. Word means 16 bits. So that's why 01 and 02 would be consumed for it. 01 and 02. That's why you got next address at 3. So you can see like how what are the number of bytes that are taken every time depending upon what representation you have. Increase would be there for a byte. So in this case 4 plus 4 multiplied by 6, 24. That's why the next address is 18 because it took those many bytes to store 24 bytes. So I actually computed this, correct? This was I think, yeah, this was what 0A 0000 0A 000000. This is my first this value 10. This is 100. This is 1000. This is 10,000. Then 1 lakh. 1 lakh. And then this was 10 lakhs. Correct? Now these are the values for DW. So 0A 002 bytes, 20 2 bytes, 30 2 bytes, 40 2 bytes, and 52 bytes. So 10. So 18 plus 10. So 18, 19, 20, 20, 19. Then 2A, 2B, 2C. Sorry, not 2A. 18, 19, 1A, 1B, 1C, 1D, 1E, 1F, 20, and then 21. Okay, then 22, 23, 24, 25. Now, if I define another variable here in data, it will start at 26. Correct? Same case here. So here, like whenever you see this representation there, this should be able to tell you how many bytes are to be reserved. So if you see 1, 2, 4, you may not be able to describe here. Like I could have written here res b4, res b2. It could have taken same thing. Correct? Let me show you that part. So we saw this res b1 actually. Okay, so let me take res 3, res b2. A4 RISB 4. Now will you be able to justify here like whether it is W or a byte? In this case we use W, one can see, but in this case if I take the same thing, what is the difference between this and this? Nothing. Nothing. But then internally it must be having some mechanism to show how the number needs to be organized. Because if I take about W, reserve W, reserve word, then I know that how 10 would be converted. But whenever I'm taking it as in a byte, when I write 10, how that 10 would be written? So 0A00, it would be sometime at some point of time, it might be difficult for me to really understand because in data it is very easy for me. I can definitely see that. When 10 is used with the byte, when 10 is used with the byte, or here when 10 use yeah here when 10 is used with the byte, so I can see that it is taking 0A. When that 10 was taken as a word, I can see that it is written like this. When it went with double, I could see that how many bytes are taken. I definitely can work out or find out whether is this 4 digit or is it the byte word or double word. Correct, but in this case, it would be difficult for me to really work out whether are you talking to make you are you making use of byte, word, or double for reserving. Correct? Will you be able to tell me like if I don't see this right side part code? Okay, suppose if I hide that, it would be difficult for us to sorry rather tell from this part like whether are we reserving which one is used there as a directive declarative, whether it is word, byte, or double. Correct? There is no difference in this case, but depending upon the representation that you have used, internal representation using Little Indian would be changing, because if it is written with a byte, then mechanism changes. If it is written with a word, mechanism changes. So ultimately I should have some way to really say understand this part. So let us try to see now what system is doing internally for you. So say when I write this, let me write nm a dot out. Sorry, program not a dot out, but program 2.o pipe. Let's now see our variables. So it is C, it is saying B, correct? This definitely is BSS section. These three are data section. These are RO data. And this is main. Correct? If I write read ELF symbol table, if I have to display, now my numbers, can they be seen? These are section headers. Let me see my symbol table. This tells me this index MHG1, MHG1. They all are written. At least these are written with a byte DB. Then something comes like it would be difficult for me to really understand now what exactly is used internally. So 2, 3, if I say byte, then maybe like, but what about them? Then I don't have anything for 3. So this might be an index at that particular position. What it says NDX. We don't know what exactly that NDX means right now. Even it would be difficult for us to really understand size. What is the size associated with each of them? Because size is said to be 0 at every time. Okay. Now I have this program 2.o. So let me generate an executable. And let me write now nm a dot out pipeless. Now try to see again your variables. BSS. Okay. Then let us see where exactly our other variables are. Yeah. This RO data. These are part data are of data section. Okay. Now let me use this read ELF. Let me see my variables. This 16 might be representing me that they are belonging to read only data. This might be telling me that this is for data section. This 24 might be telling me that it is belonging to say this is index for or a mechanism that used to represent where my data is, where my arrow data is, where my BSS is. Correct? Fine. But then what about size? We don't have any mechanism to understand really their size. Correct? So let me execute that code. It is not doing anything. So if I still see this size column for each of them still is 0 for most of my variables that I'm using. Correct? I don't have that size part defined for my variables that I'm making use of because they are defined, but they are not used. So let me try to use them in my code. If I see that code, have I used either of the variable? I have only declared because these are assigned values. That's what declared and defined. This is only defined, not declared. So let me write here. Move byte of A. Move word of A1. This is typecasting kind of mechanism. AS. Move the word of A2 10. Now let us try to see. Let us translate this code. Let us link, create an executable. Read elf-s pgm2.o. Still I can see 000, correct? So now /a.out pipeless. No, none of them is having any value there associated. Correct. Now if I execute this, nothing is happening because I haven't written any code to really show me what is happening at that side. Correct. So mechanism to deal with such kind of data at that system's end may vary from time to time. Our target is not to see this symbol table, what exactly is happening symbol table, but our target in today's class was to see this part, what mechanism is applied. Now you might see here, like when I really worked out this command to generate a listing file. Earlier, I never used anything in text code. Only one instruction was there. Now I have so many things written in my text code. So my text code got something, or my code got something here to represent. Okay, so our target from tomorrow would be to, like, I hope everybody understood now the mechanism applied here with data and arrow data, correct? Am I right? I hope each one of you must have understood this part.
Yes, sir.
Our target tomorrow would be starting from this text section. I mean to say tomorrow, I mean to say from next session. We'll try to see like how exactly we can translate the code. So we'll take different instructions side by side. Okay. So I will be making use of some instructions to demonstrate that part.